Here in question number 6, 3 rods of material X and 3 rods of material Y are connected as shown in figure. The dimensions of all rods are same. The thermal conductivity of X is 800 watt meter per degree Celsius and that of Y is 400 watt per meter per degree Celsius. If the end A is maintained at 400 degrees Celsius and E at 0 degrees Celsius, then temperature of junction B is. It is really proper for us now to draw the diagram in terms of thermal resistance. Well, if I'm saying the resistance of this part X, if it is taken to be R, then definitely the resistance of this part, that is Y, it will be taken as how much? 2R, because its conductivity is half of the material of X. So now we are having a situation here. This will be R, these two terms, this is R, this is R, this is 2R, and this is 2R and 2R. This point being A, this point being E. So looking onto the system here, definitely I would say there would not be any flow of thermal energy across this wire. That means across this wire segment will not have any thermal energy that will be crossing across here. So I would say this is R, this 2 being R by 2, and this is R. So effective thermal resistance from here to here, A to E, it is coming out to be 2R plus R by 2, that is 5R by 2. So the heat current that will be flowing across here, it will be 100 divided by 5R into 2. Okay, this is the value of heat current. Now we need to find the temperature of junction B. This is the junction B here. So this point at 0 degrees Celsius, and from here to here the resistance being how much? It is 3R by 2. So simply multiplying this part by 3R by 2 will be getting the temperature of this junction B. So here it is. This will cancel out. This will cancel out. It's coming out to be 60 degrees Celsius. So looking onto the options, here we are getting option 3 as the correct answer. Now we shall proceed to question number 7. In question number 7, two waves are simultaneously passing through a string. The equation of the waves are y1 is equal to a1 sine k x minus vt and y2 is equal to a2 sine k x minus vt plus x naught, where a1 that's been given as 8 mm, a2 being 6 mm, k is equal to 6.28 per centimeter and x naught is 1.5 centimeter. The resultant amplitude is. We need to find the phase difference of the interfering wave. That's all it is. So phase of this part being kx minus vt and this part being kx minus vt plus x naught. So effectively the phase difference would be k into x naught. Got it? So it is coming out to be k being 6.28, that means 2 pi, and x naught is 3 by 2. It's coming out to be 3 pi. So 3 pi is the effective phase difference of the interference here. So definitely they will be interfering in a perfectly destructive manner. So simply the amplitude will be subtracted. So looking onto the amplitude here, this one being 8 and this one being 6. So 8 minus 6, how much it is? It will be 2 mm. So option 1 is the correct answer for question number 7. Now we shall proceed to question number 8. Here in question number 8, a wooden stick of length 1 meter and density 500 kg per meter cube is hinged at one end in a tank of water filled up to height 0.5 meter as shown in figure. The length of the stick outside the water in stable state is. The explanation here would be the buoyancy force will be acting somewhere in between here, and it will be counterbalancing the torque because of the weight of this rod. So let's write down it as let this being the portion that is out of the water here. So about this point the weight will have the torque along this direction. So this torque of the weight, I would say, let the length being 1 meter, that is L, I'm writing it down, and area being A, density is 500 kg per meter cube. This is the mass into G, and this, let this angle being how much? Theta. So I would say it is L by 2 cos theta. This is the torque because of the weight of the rod here. Now, torque because of the buoyancy force. So this much portion is actually inside the water. So I would say torque because of buoyancy force, it will be length being how much? It is L minus X, area being A, density of water is 1000 into G, this distance being L minus X divided by 2 into cos theta. Fine. Equating these two portions, these two must be counterbalancing each other. So equating these two portions, we are having AL square G divided by 2 into 500 cos theta. This will cancel out, this will cancel out, A will cancel out, and G will cancel out. 500 will cancel out with 2 here. So we are getting L minus X whole square into 2 must be equal to L square here. Or L being how much? 1 meter. So it will be root 2. 1 minus X must be equal to 1. Or 1 minus 1 divided by root 2 must be equal to X. Question was to find out the length of the stick outside the water. So this is the length of the stick that is actually outside the water. So we are getting option 4 as the correct answer for question number 8. Now we shall proceed to question number 9. In question number 9, a capillary glass tube of radius 0.2 mm and length 6 cm is dipped vertically in water such that 1 cm is submerged in water. Height of the water column raised in the tube is. We need to find what will be the height of the water column that will be rising in the capillary tube. What we know here, height happens to be how much? It is 2s by rho gr. Just first calculate this portion. H will be 2. Here it is 75 divided by 1000. Rho being 1000 into 10, and R is 0.2 mm. That is 2 into 10 to the power 4. So this will cancel out. So we are getting this value of H to be equal to 7.5 centimeter. The question here was the total length of the tube was 6 centimeter and 1 centimeter is actually dipped into the water. So from here it should have been 7.5 centimeter, but actual length of the tube from this level is actually 5 centimeter only. So definitely the water will not pour out from this region, or the water will adjust itself in such a way the total length of the tube will be filled up with the water. So I would say option 4, 5 centimeter is the correct answer up to which the water level will rise in the tube. Now we shall proceed to question number 10. In question number 10, an object is projected vertically upward with velocity v is equal to ve divided by 2, where ve is escape velocity from the surface of Earth. The maximum height attained by the object is. We need to find what will be the maximum height from the surface of Earth that the object will be attaining. This question is yet again, I would say, just simply the application of conservation of mechanical energy in gravitational field. This height, I'm writing it down to be h. This distance, let's say it is r. So initially the particle was having the potential energy and the kinetic energy. 1 by 2 mv square has been given to be how much? Ve divided by 2. So 1 by 4. And Ve, it happens to be 2 gm by r. So it is 2 gm divided by r. This is the kinetic energy initially, minus g capital M small m divided by r must be equal to minus of g capital M small m divided by r. Fine. So this will cancel out. We are having 1 by 4r minus 1 by r is equal to minus 1 by r, or 1 by r equal to 3 by 4 r. So how much is the value of r here? It is coming out to be 4r by 3. So height will be how much? 4r by 3 minus r. So we will be getting h to be equal to r by 3. So for question number 10, we are getting option 2 as the correct answer. Now let's proceed to question number 11.